Hello! In today's video, we're going to explore a powerful way to describe movement, parametrically defined paths. Specifically, we'll focus on how to use parametric equations to describe circles and line segments. By the end of this lesson, you will be able to express motion around a circle and along a line segment using parametric equations. This means you'll be able to create equations that describe the x and y coordinates of a point as they change over time, or some other parameter. This is a key skill for AP Precalculus, as it helps us analyze motion that isn't easily described by a standard y equals f of x equation. Let's begin with circles. Circles are fundamentally about an object moving around a central point, maintaining a constant distance. This motion is best described by parametric equations. Our starting point is the most basic circle of all, the unit circle. You might remember the unit circle from trigonometry. It's a circle centered at the origin, with a radius of 1. A key relationship on the unit circle is between an angle theta and its x and y coordinates. The x-coordinate is the cosine of the angle, and the y-coordinate is the sine of the angle. To describe motion, we want time to be our independent variable, the thing that changes and drives the movement. So, we'll replace the angle theta with our parameter, t. This gives us the parametric equations x equals cosine of t and y equals sine of t. These two equations tell us the exact x and y coordinates of a point at any given time t. But what kind of motion do they describe? Let's assume t starts at 0. When t is 0, the x-coordinate is the cosine of 0, which is 1. The y-coordinate is the sine of 0, which is 0. So at t equals sine 0, our point is at 1, 0. As t increases from 0 to pi over 2, then to pi, and so on, the angle increases. This causes the point to trace out a counterclockwise path around the circle. When t reaches 2 pi, one full revolution is completed and the point returns to 1, 0. So, we found a parametric representation for a counterclockwise revolution around the unit circle, starting from the point 1, 0. Now, we can't just talk about the unit circle. How can we use transformations to describe any circle in the plane? Just like with functions, we can shift and scale our parametric equations. To get any circle, we need to consider two main things, its center and its radius. Let's call the center h, k, and the radius r. Think back to the unit circle. X-coordinate is cos t, y-coordinate is sine t, the radius is 1, and the center is at 0, 0. To change the radius, we multiply the trigonometric functions by the new radius r. So, our new equations become x equals r times cos of t and y equals r times sine of t. To change the center from the origin to some new point, hk, we just add h and k to our equations, respectively. This gives us the general form for a parametric circle. X equals h plus r cos of t, and y equals k plus r sine of t. This describes any circle centered at hk with radius r. Let's work through a quick example. Let's find the parametric equations for a circle with a radius of 5 and a center at -2, 3. First, we identify our values. The center, hk, is -2, 3, so h is -2 and k is 3. The radius r is 5. Now we plug these values into our general equations. X of t equals -2 plus 5 cos t, and y of t equals 3 plus 5 sine t. These two equations now trace out that specific circle as our parameter t changes. Just like we saw earlier, this path traces out the circle counterclockwise, starting at the point h plus rk, which in this case is 3, 3. Now let's switch gears from continuous loops to straight paths. We'll learn how to parametrize a line segment between two distinct points. A line segment is defined by two endpoints. Let's call them P1, with coordinates x1, y1, and P2, with coordinates x2, y2. The beauty of parametric equations is that we can describe the coordinates as functions of a single parameter, t. Our goal is to create equations xt and yt that guide a point from P1 to P2 as t changes. There are many ways to do this, but one of the most intuitive is to think of it as starting at the first point, P1, and then adding a little bit of the vector that connects P1 to P2. The vector from P1 to P2 represents the total change in x and y needed to get from one point to the other. The change in x is x2 minus x1, and the change in y is y2 minus y1. Let's call these delta x and delta y. We want to scale this vector by our parameter t so that when t is 0, we're at p1, and when t is 1, we're at p2. This gives us the general form for a line segment. The new x-coordinate is the initial x1 plus t times delta x. The new y-coordinate is the initial y1 plus t times delta y. By limiting our parameter t from 0 to 1, we ensure we only cover the segment between p1 and p2. Let's test this. What happens when t equals 0? Plugging in 0 for t, we get x of 0 equals x1, and y of 0 equals y1. So, at t equals sign 0, we are at our starting point, p1. This works. What happens when t equals 1? Plugging in 1 for t, we get x of 1 equals x to 1 plus delta x, which is x2, and y of 1 equals y1 plus delta y, which is y2. So at t equals sign 1, we are at our endpoint, p2. This also works perfectly. So, by varying t from 0 to 1, this parametric form gives us every point along the line segment from p1 to p2. Let's put that formula into practice with a concrete example. Suppose we want to find the parametric equations for the line segment from the point 1, minus 2 to the point 5, 4. First, we need to identify our components. Our starting point is p1, 1 minus 2. So, x1 is 1, and y1 is minus 2. Our ending point is p2, 5, 4. So, x2 is 5, and y2 is 4. Next, we calculate the change in x and the change in y. Delta x is 5 minus 1, which is 4. Delta y is 4 minus negative 2, which is 6. Now we can substitute these values into our general parametric equations. Remember the formulas: x of t equals x1 plus delta x times t, and y of t equals y1 plus delta y times t. Let's find the equation for x of t first. X of t equals our starting x value, 1 plus our change in x, 4 times t. So x of t equals 1 plus 4t. Now for y of t. Y of t equals our starting y value, minus 2, plus our change in y, 6, times t. So y of t equals minus 2 plus 6t. We have our two parametric equations. But we're not quite done. We need to specify the domain for our parameter t. To describe just the segment between our 2 points, t must range from 0 to 1. This pair of equations will trace the path from 1 minus 2 to 5, 4, as t increases from 0 to 1. So, we've now covered how to describe circles and line segments using parametric equations. Let's quickly recap what we've learned. First, for circles, we started with the unit circle, x equals cosine t, and y equals sine t, which gives a counterclockwise path starting at 1, 0. We then generalized this by scaling for a radius r and shifting for a center, hk, giving us xt equals h plus r cosine t, and yt equals k plus r sine t. Next, we parameterized line segments from a point p1, x1, y1, to p2, x2, y2. The formula we used is xt equals x-1 plus x2, x-1, t, and yt equals y1 plus y2, y1, t, with the parameter t restricted to the interval from 0 to 1. This gives us a powerful tool to describe motion and geometric shapes that is more flexible than traditional Cartesian equations. You are now able to construct these parametric descriptions for both circular and linear paths. Thank you for watching, and I hope this has helped you understand parametrically defined paths.